This video is going to look at the definition of the derivative, so we're going to focus on that and hopefully get a good feel for what a derivative is and how it relates to rates of change. So going forward, the definition of the derivative is that it is the instantaneous rate of change. So we talked in the last video about how to calculate the rate of change, both average and instantaneous, and this one is looking for that specific instantaneous rate of change. And so this can be expressed in several ways. There's many ways, again, that we can write it. So one is f prime of x. So this notation means the derivative of the function f of x. We can also write it as y prime. We can also write it as dy divided by dx. And we can also write it as d by dx of f of x. And this is assuming that y equals f of x. So all four of these are different ways of writing the derivative, but they all mean the instantaneous rate of change of the function y equals f of x. The definition, or like how we can write that mathematically, means that, or sorry, let me restart that. This definition being the instantaneous rate of change means we can define it for a specific point or for the entire function. And so we can have the derivative function defining the instantaneous rate of change for every point on the original function. So what this means is I can either write, if I'm talking about a specific point, the derivative of f of x at x equals a is blah, 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 and then I give some number. Or I can say the derivative of f of x is dot, 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 and then I'll be giving a function that defines the derivative at every point in space. So moving on with that, that derivative function is what I just talked about, where I say the derivative of f of x is, defines the, oh, this is kind of replicating what I had before, the instantaneous rate of change at every point. So for example, if I have the function f of x equals x squared, the derivative of this function, you don't need to know how I get it, don't worry about it for now. The derivative function is the function 2x. So this is our original function, this is our function 2x. So what this means is the instantaneous rate of change of f of x at, say, let's pick 1, at x equals 1, is 2 times 1, which equals 2. At x equals 2, it's 2 times 2, which is going to be 4. At x equals 10, it's 2 times 10, which equals 20. And this kind of makes sense because if you imagine this, it's a parabola, and so we expect as x gets bigger and bigger and bigger, the instantaneous rate of change gets steeper and steeper. The y values are changing much faster as x gets bigger and bigger. So here's our definitions. Using what we defined earlier for instantaneous rates of change, we have two forms. This first one is the general form, and this second one is an alternate form. This alternate form only works when we're looking at a specific point, and this is actually a mistake. this should say as x approaches a. So in this first one, we want to make delta x smaller and smaller and smaller. And on the second one, we want to pick x values closer and closer to a. This can define the derivative function. And this second one can define derivative at a point. And that's really why we have the two of them. The second one tends to be a little easier to work with if you're trying to find the derivative at a point. And the first one tends to be more generalizable, but maybe a little bit trickier to work with. So we're going to pause here, and then I'll have another video that looks at a couple examples.